So on Monday at 4 p.m., I made a remark that we all should know these advantages. Make sure you know them over the AA. Every instrument has an advantage over another. So remember, AA is very specific for metals, right? AA is very specific for metals. Although you can push it to the vacuum, but it's normally, we use AA for the measurement of metals. So the advantage of using emission spectrometry over atomic absorption is these advantages. You can measure several elements simultaneously, and multi-elements can be analyzed from a very small sample. Not so with AA. AA, you need a lot of sample, and you need tedious preparation, right? So you might need tedious preparation. The whole idea of preparing samples for emission spectrometry and for AA, atomic spectrophotometry, nearly follows the same procedure. Okay? But a little bit more tedious in one case. Now, you can see low concentration refractory compounds can be determined. We gave examples last time in AA of calcium hydroxide species and some spectral lines interferences. So that lower interelemental interferences because of a higher temperature. Then we say non-metals can be determined by plasma sources. Very high concentration range. The dynamic range is very high usually, okay? So this is just a reminder on what we talked about here. We also talked about the disadvantages of emission spectrometry. Although it has those advantages, there are some disadvantages. It's more expensive equipment that is needed. Maintenance is expensive. So for example, it consumes a lot of argon, so you have to be buying the argon. The procedures are somewhat complicated than absorption methods. If the procedures usually, let me give you a typical example of a procedure that we use in the lab. For example, you take your sample, you dissolve it in acid, nitric acid. In this sample, for example, if it is fruit samples, soil samples, or even blood samples, you have to digest them in acids, okay? They can be acids like nitric acid and HCl, depending on which chlorine may have some interference sometimes with other elements, but that depends on the kind of method that you're using, whether you're using inductively coupled optical emission spectrometry or inductively coupled mass spectrometry. Now, you use the mineral acids that we normally use. And let me tell you, there is one more thing that you introduce. You introduce, for example, hydrogen peroxide to digest the organic matter, right? So you have one of that step. And also there is going to be also adjusting the concentration. We usually take several hours of digestions, usually. It can take several hours to finish the sample. So the procedures are somewhat complicated. The procedures are somewhat complicated than the absorption method. And even setting up the method is not as simple as AA, but it's doable, straightforward. And there is more operating cost than absorption techniques. Remember, for AA, you only need the holocathode lamps, and they will be there for quite some time until they burn out. And then for emission spectroscopy or spectrometry, you're going to need to replenish the argon. That is a major cost in your analysis usually. What about? Yeah, but it's easier than. For AA, you have to replenish it, but that is manageable. The cost is lower. An argon tank costs more. And you need, it actually consumes much more argon usually for one run. So for example, the one we have there, you can buy liquid argon or gaseous argon. Okay? So like the one there, if I use it for 2 hours, and one of my colleagues, another professor, uses it. So if I have 60 samples, all right, I'm running it for 60 samples, straight 2 to 3 hours. So that means I will deplete that tank by about a quarter. And if another professor uses it, again, another quarter. You see, you've gone to a half, right? So again, if we continuously use it like we have done previously, normally we have to, that's why you have 4 tanks there. One of those tanks will be depleted, then it will kick into the standby tank. So let's say you're going to need about 2 tanks. If we were doing continuously every day, like the labs that are very active labs doing analysis for either clients or their research all the time, then we should be replacing those tanks per week. We are going to run 1 tank per week or 2, depending on how many samples for how long. So it's more expensive, more operating cost than the absorption technique. So those are some of the advantages. However, there is this note here. You notice that note, atomic emission and absorption methods are complementary to each other. You see that? Atomic absorption and atomic emission are complementary. It does very well in some instances, many instances. So, for example, if you want to analyze metals, multi-elements, then you have to go to the atomic absorption. There are times, for example, I've analyzed metals like cadmium, and I don't feel I'm getting a good reading from the emission spectroscopy, inductively coupled plasma. Then I run it on the AA. All right. So those are some of the disadvantages, as I've mentioned. I want to start from here on the inductively coupled plasma source, inductively coupled plasma source. So the figure that I showed you last time, let me bring that figure up. So this is the figure that I wanted to start with. So you can see there the inductively coupled plasma, and you see the torch. You look at the torch, actually it's because of the argon cations and the electrons. It looks like a torch, actually. So this torch here has 3 concentric quartz tubes. There's the inner core tube, there's the surrounding jacket of quartz tube, and there is the outer jacket of the quartz tube. So you want to see this one, the inner one, where you see the arrows. You see the arrows there. So that's where the sample aerosol or vapor is argon. For example, I believe most of you were there. Were you there? Mr. Brock was there, Josh and Nelly. Michael, if you were not there when I showed you the instrument, okay? So, and those of you who are online, those of you who are there, you notate that from one side, you have a nebulizer. You saw the autosampler, right? You saw the autosampler. And so the autosampler brings in the sample into the nebulizer. Then you have the aerosol that is then led into the torch. So we are talking about this arrow here, the sample aerosol or vapor in argon. Then there is also, you see, this is the inner jacket there. Then there is this second one here. And there is a third. Now you see there is a tangential argon plasma support flow. So argon has to be there all the time. Now, you notice there is this arrow here or this circle here showing something like an electric field, that's a radio frequency, okay? So there is a radio frequency induction coil at this end, but all of this, you want to see, in this is what we call a typical ICP source, the whole setup, electrically coupled plasma. So let me back up here. So this is the figure that is referred to here, a schematic of a typical inductively coupled plasma source, what we call a torch. And it consists of 3 concentric quartz tubes through which streams of argon gas flow. At the same time, the diameter of the largest tube is about 2.5 centimeters, and surrounding the top of this tube, as you see, is a water-cooled induction coil. The radio frequency coil has to be cooled. So it's powered, that induction coil at the very top is powered by radio frequency capable of producing 0.5 to 2 kilowatts of power, and the radio frequency of about 27 or 41 megahertz. So notice the other thing, we call it emission. That torch is critical. We call it emission because of what happens there. The ionization of the flowing argon is initiated by a spark from a Tesla coil. Now, what I did not show you is when we use the ICP, we turn the torch on. Are we together there? I did not turn the instrument on. There are buttons there where you turn it off, you turn it on. So those buttons, you turn it on, then you're turning on the a spark from the Tesla coil. You turn on the Tesla coil by just turning it on. It's connected to electricity. And at the back of it, remember, it is, you have water, you have the coil there, water-cooled induction coil. That also has to be there, okay? I did not open the instrument at the back panel to show you there are some of these electronics that we have to turn on. So then you can see that is what that is. Now, again, this is a repetition of what I have said. This slide is a repetition of what I've said. In ICP, the plasma is created in the argon, and a few argon ions are formed. And these ions absorb energy from the radio frequency field, and they are accelerated and moved in the closed annular path. So then collision between the higher energy argon ions and free atoms, notice you create the argon ions, a few. Now, those argon ions, you can see there is collision between higher energy argon ions, and the free atoms generate more argon ions. That is what forms the plasma. So here you have the sample, and you have argon ions, a few of them, the cations, that is, and they are now going to collide with the sample atoms, and so you now generate more argon ions. The temperature of the plasma is about 10,000 K or about 5,500 degrees C. You know how to convert degree Fahrenheit to degree C, okay, and to Kelvin ultimately. The sample is introduced in the central tube, as you see, and the argon cooling gas is applied to keep the tubes from heating. So that is the basics of, you have to have usually, and this maybe I should have shown you, at the very back, we have a sink where we let the water to cool the argon tubes. And the radio frequency is water cooled. You can see there in the region about 10 to 30 millimeters above the core. You see here, this is where the radio frequency, a lot of ionization is going to occur here, because you're ionizing there, you're ionizing the atoms by radio frequency. So the plasma above about 10 to 30 millimeters, the plasma is transparent. You can actually see it when you look at it. When we turn it on, you can actually see it. And the region 15 to 20 millimeters is typically for spectral observation. So you notice there 15 to 20 millimeters, that's where the spectrum is observed. And now let's see. You notice the residence time. The residence time for the sample in the plasma is very short. How short? You see that? 2 milliseconds. Milliseconds is short enough. So, but there is that quick ionization. And so you would see that sort of the sample colliding with the argon tubes. I know some of you may work in this area because you might find a job here. I'll tell you, when you are looking for a job, you might find for those labs that are doing some analysis, they are going to train you on the inductively coupled plasma. I remember one of my students, Matthew Parks, that is where he found a job first before he moved into the biological area. Okay, so I mentioned that to help some of you see that if you know this, each one of these analytical techniques that we have covered, from chromatography to spectroscopy, when you go for an interview, then it makes it easier for people to know you have handled it, you are trainable. Are we together there? You're trainable, and then they can take you in. They would ask you, have you written a report? Have you prepared your standards? How do you do it? Okay, do you know how it works fully? I know a little bit, but I can learn. All right, again, this is now the sample introduction in ICP. Similar thing. Notice you have here, you have the sample introduction into ICP. You have a sample from the auto sampler, and you have here, notice here, you have the aerosol. Notice the way that's how it looked like. The aerosol from the sides. So you form that aerosol. You can see there, that's the aerosol. And then there is a drain. We actually have a drain as it's being cooled. And then it goes in here, then you turn on, there is an auxiliary plasma argon. So you have two tanks, there is auxiliary that's going to kick in case one of the tanks, the argon tanks, is depleted. So there is the plasma argon, you can see it here. There's one of these. Then there is the auxiliary argon, which is optional, but you don't want it to be optional unless you know your samples are going to use all the argon. But sometimes we let it so that if the pressure is low in the tank, it kicks in. And then you go to the optical path here. And this is how it looks like actually when you look at it, this diagram. That's how it looks like. It looks like a flame, but it's the argon atom, cations and the electrons that you're seeing generated in the radio frequency. So those, what I'm pointing at, those are the radio frequency. Any question here? So then we are talking about the introduction of the sample into the torch, the resulting ions and the associated electrons usually then interact with the fluctuating magnetic field produced by the induction coil. So you saw that line for the electric field. And the interaction causes the ions and the electrons within the coil to flow in the closed annular paths, because you have an electric field. So that is what is causing those annular paths. And you have the temperature of the plasma that is formed with this electric field, and the plasma is high enough to require thermal isolation of outer quartz cylinder. So usually there is the inner quartz where you have your sample, and there is the induction coil there. So the temperature is high enough. So you need to isolate the outer quartz cylinder. This isolation is achieved by flowing argon tangentially. You flow the argon. Remember, some of you might ask, what's the use of this tangential argon? So you want to cool the inner tubes around the walls of the tube, as we saw. Okay. So sample introduction, remember, in all instruments, every instrument, you have to introduce the sample. So sample introduction So samples are carried into the torch by argon flowing at a rate of 0.3 to 1.5. You see the numbers there? 0.3 to 1.5 liters per hour. Is there anyone imagining how much that is? Liter per minute? That's a high consumption rate. Yeah. This is not a liter. I'm holding something here. Almost. Right? If I fill it. So we are consuming per minute that much, right? So that's a lot. And so if you think the tank, then you are consuming a lot of it, actually. So this is 0.3 to 1.5 liter per minute through the central quartz tube. And samples are introduced into the argon flow by nebulizers. We have various new nebulizers as you saw last time. And then as you introduce the sample into the argon flow by nebulizers, then you have the sample is nebulized in a cross flow nebulizer by a stream of argon. Now, this is only one. Remember, you can introduce samples in as liquids. That's the most common. But you can also introduce samples. Samples can be introduced as liquids. They can also be introduced as solid samples. So solid samples remember how you introduce solid samples in AA? How do you introduce them? Just the graphite furnace. Electrothermal means furnace is one most commonly used. So you can also introduce samples into the plasma via electrothermal vaporization. So through the furnace. So here again, we have this, it's the same kind of repeat. So I don't need to repeat this. All right, we have already said about this. And one more thing here, the electrothermal vaporization is good for both liquid and solid samples. And then there are ablation devices as well. So ablate it just to, so this is good for solid samples. You put a solid and you flow in. On the surface of it, you get either a laser or you get a sharp from the surface, then you can get the atoms from the surface. That's ablation. So there are other methods that you can introduce your samples into the argon.
Sorry, what did you say ablation was?
To ablate means, I will demonstrate it here, right? If this is a solid, Mr. Brock, this is a solid, you can either send a laser to just etch the very top. To ablate means just take a small surface off.
Okay.
Yeah. Okay. So just take molecules, atoms from the surface of whatever it is, whatever solid. Whatever you can use to do so. You can use a laser, you can use a sharp flow of air if it can get off the atoms from the surface. All right. So electrothermal, again, you can imagine if you're going to do the electrothermal type of introduction, you have to, if you use a graphite furnace, you have to couple it in such a way that you have the furnace coupled to the plasma, not the plasma, the nebulizer, just like what we do in AA. You have to make that setup. Okay? So electrothermal vaporization coupled with a plasma torch offers microsampling capabilities and low detection limits of electrothermal furnaces. By the way, graphite furnace AA has low detection limits And that's why if you couple it with the ICP, then you lower the detection limits much more. Okay, so while notice in electrothermal graphite furnace by itself, it has low detection limits. And then it has low, the linear range comparatively is low, the linear range. I'm talking about the linear range, comparative linear range. So there is a wider linear working range for ICP. And so you have those two advantages. Now you can then lower the detection limits, and the dynamic range is expanded when you couple electrothermal vaporization with ICP. And then there is the freedom from interference, and then the multi-element capabilities of ICP. So what we are saying here, although there is some interference, but comparatively, the interferences between the elemental interferences in an ICP is much lower compared to atomic absorption, okay? Because you're working with a plasma with various lines. Okay, now the plasma appearance in the spectrum, usually the typical plasmas are very intense, brilliant white, non-transparent core topped by a flame-like tail. And the core extends a few millimeters above the tube. We have talked about those millimeters, okay? So that is made up of a continuum, which is superimposed to the atomic spectrum for argon. So again, the source usually, so that's how it appears. Let me go to the next thing. So we have talked about the various, are we together there? So we have talked about these 10 to 30 millimeters, and then 15 to 20 millimeters above the induction coil. Okay. So many of the most sensitive analyte ion lines in this region, about 15 to 20 millimeters region of the plasma, are free from the ions. But you can form ions. But in this region, it's found 15 to 20 millimeters. Those, when you observe the plasma, or you take your measurements between 15 to 20 millimeters, then you minimize the cations, such as calcium +1, calcium +2, cadmium +1, chromium +2, and manganese +2 ions. Any question here? So then we have talked about sample introduction. Now, how do you analyze? There is, talk about the advantages of ICP over atomic absorption. Now, normally, you want to operate at given temperatures. So now let me get to the figure itself, then come back here. So the figure, this is the figure, ICP temperatures. You know, these ICP temperatures, the viewing area for each element is typically reported as millimeters above the load coil. So above, notice here, the height load. So 15 to 20 millimeters above this plasma. So this is where you want to observe, or where the radiation should be. Now let's see here. Now notice the temperature starts at the very hot temperature here, where you have the radio frequency, 10,000, 8,000, 6,800. Then you go 6,500, 6,200. So this is temperature in Kelvin plus or minus 10%. So again, to the very top, 6,000 Kelvin. So normally you have the sample aerosol, and so the temperature is normally very uniform. So I want to go back so that we see. So this figure here that we have seen shows the temperature at various parts of the plasma, and the sample atoms would have resided for about 1 millisecond, 2 milliseconds at temperatures ranging from 4,000 to 8,000 Kelvin. So the sample itself, millisecond, is 1, 2. Those are 2 milliseconds, right? But very fast. So normally, that residence time, these times and temperatures are roughly 2 to 3 times greater than those found in the hottest combustion flames used in flame methods. So flame methods, whether they are hot, the sample usually stays for longer. And the times and temperatures are roughly 2 to 3 times greater. So which means 2 to 3 times greater than found in the combustion tubes in flame methods, which means the sample itself stays there for longer in ICP. So as a consequence, atomization is more complete and fewer chemical interference problems arise. And so surprisingly, we would expect a higher temperature, but surprisingly, ionization interference effects are very small or non-existent. This is what goes against what we know. Normally, we would think if it's a hotter temperature, you are likely to ionize it, all right? But it's very surprising that at these temperatures, 4,000 to 8,000 Kelvin, much higher than flame AA, the ionization interference effects are very small. They are nearly non-existent. Because of what do you think that will be? Remember, there are argon cations and electrons. We understand why that's the case. Remember, for ionization, you have to produce electrons. So the production of electrons pushes the equilibrium to the left, all right? So that you have gaseous atoms there. So because the electron concentration from ionization of the argon is large compared to the resulting from the ionization of sample components. So this large buffer of electrons that is produced from argon shifts the equilibrium to form the atoms to the left, so to say. We have talked about several advantages associated with the plasma source. So we have talked about this. So let me go ahead and talk about the applications. Remember, we listed the advantages. There are quite many, right? So now the application of plasma sources. Plasma sources are rich in characteristic emission lines, which makes them useful for both qualitative and quantitative analysis, but for both qualitative and quantitative elemental analysis. Now, here's the point. What we use AA for? AA, atomic absorption, either in the flame or in the electrothermal analysis. What is AA, atomic absorption, used for? For what? For metals. Is that what you said, Mr. Bro?
I said percent composition.
Yeah, but specifically, it's metals, right? It's metals that are analyzed. Whereas in ICP, you can analyze metals and what? Non-metals. And now you notice here, there is the ICP brings another advantage. You can access many more emission lines. So if there is an interference from one line, you can choose another one. Are we together there? That is if you are using the wavelength. ICP optical emission spectroscopy. The same is true of if you replace, for example, optical emission, if you replace wavelength with the mass spectrometer, then you also can choose a given mass that you're going to use for zinc and so forth. Okay, like what we have in here in our department is ICP mass spectrometer. Okay, so the inductively coupled plasma yields significantly better quantitative analytical data than other emission sources do. And do you know how old ICP is? ICP is not very old. It's in the 90s, like many other methods. Okay, so the papers that you might read would be from mid 80s to the 90s. That's when it's active, still active today. And one other thing I needed to mention here when I asked the question on what AA is good for, it is for elements. Atomic absorption is for elements, all right? Doesn't mean you cannot analyze, mostly it's for elemental analysis. Now for emission, we also use it for elemental analysis. Most often, you want to know is copper here, is potassium here in this sample, and so forth. So now, it offers better quantitative analytical data than other emission sources. So the excellence of these results stems from their high stability, low noise, high stability, low noise, low background, remember, and freedom from interferences. The background does not interfere so much, whereas in the others, there is interference from the background. These are advantages. So we have all these applications. And if people have money and to spend, that is where you invest in. If you have a company that is doing elemental analysis, you can set up a company that is doing analytical elemental analysis. There is a larger turnover in terms of your money, then you invest here, right? Together here. You set up a lab, and the government would give you a license to operate. You get a technician or a technologist to run this, all right? You can run it. And most people will say, hey, here is our lab that does good analysis. Let's send our samples there. That's how you get a name. So the other thing is, now we've talked about sample introduction. Let's talk about sample preparation. Sample preparation, usually inductively coupled plasma emission is used primarily for qualitative and quantitative analysis of samples that are dissolved or suspended in aqueous or organic liquids. Now, in this class, I don't tell you about the other details on the type of lenses. It suffers from solids because you have to change the torch all the time because you form solids. Now, with plasma emission methods do exist for direct analysis of solids. We've said that these procedures include electrothermal analysis. The same preparation, similar type of preparation that you're going to do in AA, but a little bit more rigorous. Now, elements can be determined in principle. All metallic elements can be determined by plasma emission spectrometry. Now, just like what we said earlier, we mentioned this earlier on, actually. Okay, I'm just repeating. We mentioned this. A vacuum spectrometer is necessary for the determination of nonmetals, and which ones, such as boron, phosphorus, nitrogen, sulfur, carbon, because the emission lines of these elements lie at wavelengths below 180 nanometers, below the UV region. So they occur in the vacuum region. So this is where these elements have absorption lines. And so the usefulness for the alkali metals is normally limited. Why? Why is it limited? Think about the process. Why is it? We can use it for these alkali metals, group 1A, but normally it's limited. It doesn't mean we can't analyze it. That's all I'm saying. But most often we use it for these other metals which are other than group 1. Why is it limited? Can you think of a reason? Low variance electrons, what does that mean?
This group one only has one valence electron, but excite as much.
Yes, that's the word. Excited much faster, right? So you can form ions quicker. But that doesn't mean you can't push the electrons back and then have the metals have done that a number of times, many times. So the plasma emission is generally limited to the determination. I think this statement is outdated. Are we together here? 60 elements is outdated. You can actually analyze most of the elements. If you look at the table I gave you earlier, it's much more than 60. So again, in emission spectroscopy, you're going to have a calibration curve, like all analytical methods. You must have calibration curves of plasma emission. And usually, remember, the dynamic range is big. It's 10 to the 6th sometimes. So how do you plot a million on your graph? The dynamic range is greater than for AA. So normally what we do is we plot a log function, which we're going to see is when the range of the concentration is large, log plots are employed instead. So you put log plots usually because of the greater dynamic range. All right, so we have said you prepare calibration curves and then detection limits. Let's talk about detection limits here. I've given you a handout there, right? You can see that handout. Let's compare. I want to share this. Those of us who are online for us to see. This handout is from Park Nelma. They are advertising their AA world leader in AA, ICPOS, and ICPMS. I've taken this from there. There is a newer version. It's in blue. This is an older version, but the same information actually. They have not changed anything other than color. Now you can analyze. Look at what you can analyze. Let's expand our view. All right. There. What else can you analyze? You can see that in the pharmaceuticals. What else can you analyze? Why is that there? Michael. A whole view of fields and whatever, grass and whatever it is, right? Plants. And so look at what you can analyze, tablets. And now fruits. And so here are the elements here, periodic table of the elements. Then you can analyze how it works. See there. Now I'm going there, fruits and so on. Many things that we can deal with, selecting a technique for your analysis. Now, quickly, let me zero in on what I want to show you. This is the table, atomic spectroscopy detection limits. You can see that. Look at these detection limits here. So we have the elements, flame AA, we have the hydride, that's for mercury, you can see Hg. You have GFAA, what is GFAA? That's graphite furnace. We can see ICP-OES, ICP-MS. We see, again, those are the three methods compared. And so you can see a list of elements all the way from, you see, potassium, lithium is there, potassium is there. Although we say it's limited, you can use it for those metals. Now, because of time, can I pick this up on Friday? And I will finish this up. I'm about to, a few more slides, finish up this, then move on to chapter number, I think it's number 13, okay? That's where we move to. Okay. I want to go over this slide to draw the point home that the ICP-MS competes with the graphite furnace in terms of the detection. We'll stop. I remember we have a quiz on Friday that's going to cover information on AA up to where I've stopped, advantages, disadvantages, and how to do ICP type of determinations. Yes. Most of that, just general information. Just be prepared.